Okay, chapter 9, which is on simple harmonic motion. So in this chapter, you will have 3 subtopics. So the first one is on kinematics of SHM lah. So in this subtopic, you should be able to explain what is simple harmonic motion, solve problems related to the SHM displacement equation. Derivation, you don't really have no, you have to derive and apply the equations lah, because sometimes they just give you the displacement punya equation, then you have to derive sampai dapat velocity and acceleration lah. Okay, and then kinetic and potential pun lah sama juga, and then emphasize the relationship between total simple harmonic motion energy and amplitude. And then lastly, you have to apply this for untuk SHM punya problems lah. Okay, so what is actually simple harmonic motion? So the long definition is, it is defined as a motion without the loss of energy. So it is moving without the loss of energy, in which the acceleration is directly proportional to its displacement. Okay, so the acceleration is directly proportional to the displacement from the equilibrium position. So dia ada fixed point yang equilibrium lah. Okay, and then it is directed towards the equilibrium position, but in opposite direction of the displacement. Or mathematically, you can just write it down like this, and know that just know that the negative sign only indicates the direction of acceleration. Okay, it's the definition. It indicates the direction of the acceleration, which is always opposite to the direction of the displacement lah. Okay, so examples of simple harmonic motion are simple pendulum, vertical and horizontal spring oscillations. And in short, you can basically get an idea that this SHM motion is a motion that repeats over and over without the loss of energy, and then it has a stable equilibrium point. Stable equilibrium point means it can go back to that point. Okay, so for example, if in this case, if the object is placed somewhere here, you can't actually, if it moves pun, you can't actually get it back to this position balik, sebab dia akan terus turun pergi bawah, so it will not come back to this point. But if it's at this point, you can actually, the motion repeats over and over again, and then it will always go back to this equilibrium point. Okay, so why is it in motion? Is because there is a force known as restoring force. Okay, so restoring force ni dia punya tendency untuk restore the spring to its equilibrium position. Okay, so tendency for it to restore dia punya original position. Okay, and then this force is proportional to the displacement from equilibrium and always directed towards the equilibrium. Contohnya kalau kita tengok yang ini sekarang ni, so the force exerted by the spring is exerted by the spring acts to the left lah. Okay, maksudnya kalau kita tarik ni block to the right, the force will try to restore it back to this position where it is at equilibrium. Okay, so sama jugalah kalau dia di equilibrium position sudah, dia tiada restoring force. I mean, the restoring force equal to 0. Okay, and then if dia moves to the left pula, the spring is compressed now, the restoring force will go against the motion of the spring. I mean, it will try to restore it again back to the equilibrium position di sini. Okay? Alright, lepas tu. Alright, so this is the terminologies in simple harmonic motion that you have to know. So we have amplitude, which is the maximum magnitude of the displacement from equilibrium position. Okay, so it has an SI unit of meter. And then we have period, which is time taken for one cycle. Make sure you know it is for one cycle. And then the SI unit is second. This is the formula. And then we have frequency, which is the number of cycles in 1 second. Okay, in 1 second. The unit is hertz. And lastly, we have angular frequency. It is also known as angular velocity ataupun omega. Okay, so this is the number of cycles per unit time in angular unit. Angular unit means it is in radian per second lah. Okay, so this is the formula given here. Okay, so now we are going into kinematics of simple harmonic motion. So here we have displacement. We have displacement, velocity, acceleration, what else? Itu je. Okay, so the first one is on displacement. So displacement, kita label dia as x lah. Okay? So we know that the acceleration is always directly proportional to the displacement. Okay? And then we know that the negative sign indicates the direction of the acceleration to be always opposite to the direction of the displacement. So in this case, the negative sign can be excluded during calculation. Okay? So dia boleh excluded from the calculation. So these are the examples. So equilibrium point ni bila dia tidak move lah. Okay, so at this point this is the equilibrium point, this is the equilibrium point, and then this one is the equilibrium point. So we will only be focusing on these three situations. Okay, and then what else should I say? Okay, so this is displacement. Okay, now we go on to dia punya general equation of displacement. Okay, this is important. You have to know the general equation of displacement as a function of time. Okay, so this is a diagram showing that if an object is moving in a circular motion, so this is a circular motion. Okay, so lepas tu dia akan move, dia akan move in one cycle lah. Okay, see this 360 degree ni maksudnya dia sudah move one cycle. Okay, so if we see point A di sini is the amplitude, which is it is the maximum displacement yang dorang dapat. This object can move. So this is the amplitude. Lepas tu you have to know one period. A period is one cycle. Okay, so the time taken for one cycle. So ini baru considered as one cycle lah. This is not one cycle. No, yeah, it has to be macam ni baru considered as one cycle. Okay, so we will have negative and positive amplitude lah sebab sekarang ni dia ada sine graph. Okay. Okay, so if an object starts at equilibrium point where x is equal to 0. Okay, di sini dia starts at x equal to 0. Kita punya general equation of displacement is x equal to a sine omega t. Okay, so omega t is also known as the phase lah. Okay, phase angle. Phase angle. It is also known as phase angle. Okay, lepas tu kalau dia pula start from positive or negative amplitude, kita punya equation will become cosine. Okay, so a cos omega t. Okay, kalau cos maksudnya dia akan start dari sini turun macam ni. Okay, so starting point ni dia bukan equal to 0. No, dia akan start dengan the amplitude. Okay, okay, so that is the equation of displacement. So make sure kamu tahu ni. So these bits are important, really important. Okay, now we go on to velocity. So from the definition of instantaneous velocity, we know that the velocity is the rate of change of displacement. Okay, so the rate of change of displacement where we have this equation for displacement, which is a sine omega t. So if we derive this equation, we will then get the velocity punya general equation. Okay, so this is the general equation pula untuk velocity. Okay, so derivation there is just basically derive the equation for x displacement untuk cari velocity. Okay, and then you should also know that the maximum velocity occurs at equilibrium point. Okay, so make sure you know that maximum velocity occurs when displacement is equal to 0, i.e. the equilibrium point. Okay, so in order for us to calculate that, we have the formula here lah. Okay. Right, lepas tu what else? SI unit there is meter per second. And then this is the relationship between velocity and displacement. I think this is given in your formula sheet. Just make sure you know how to use the equation lah. Okay. So this is for velocity, and then now we are going on to acceleration. So acceleration is the rate of change of velocity. Okay, so sekarang kita substitute lah V, derive this equation supaya kita dapat acceleration punya equation. So kita akan dapat this value here, this equation here, in which we can actually see that the A sine omega t is actually equal to the displacement punya equation, A sine omega t, which is the definition for simple harmonic motion. Okay, so that is the relationship lah between acceleration and displacement. This one is for velocity and displacement. Okay, right, let me check if the theory. All right, okay, examples we go on to later. So this is for energy in simple harmonic motion. Okay, so we are gonna be focusing on two types of energy untuk this chapter. So for simple harmonic motion, the total mechanical energy is constant. Okay, so E K plus U equal constant. So they will be constant. So as the object oscillates, so if they're dari equilibrium ni, they oscillate back and forth, the energy converted from potential to kinetic energy. Okay, so potential energy punya formula is just this one, and then for kinetic energy, the punya formula is this. Okay, we know that the maximum speed occurs at equilibrium point, right? So it occurs at equilibrium point. So at this point, the total energy is kinetic. Okay, so the total energy left at that point is only kinetic energy. Okay, so dia tiada zero potential energy. Zero potential energy. Kenapa dia zero potential energy? Sebab sekarang ni dia back to dia punya equilibrium point. So why would they have potential energy? It is left with kinetic energy sajalah. Okay, so kita akan left with, oh wait, I feel like I've written the wrong equation. Oh yes, okay, I'll edit this later. It should be U equal to half m omega square x square. Okay, this one is for kinetic energy. Patutlah macam pelik. Okay, so this is the formula. I'll edit this later for your notes. Okay, so at x equal to 0, which is at equilibrium point, we will then get the energy punya formula to be equal to this. Okay, and then the maximum displacement of the body is what we know is to be the amplitude. Okay, so that is the maximum displacement, which is the amplitude. Okay, so at amplitude, the motion changes direction, right? So the motion changes direction. For example, if this is the pendulum, at this point, it will reach its maximum height. Okay, maximum amplitude. So what happens during maximum amplitude ataupun maximum height? We know that the velocity will equal to 0. Okay, so when the velocity is equal to 0, it will then change direction. Okay, so that's why there goes back and forth. Okay, so at this point, velocity is equal to 0. So what energy is left? We will then be left with just potential energy. Okay, so in that case, we then get the formula again to be the same, which is this formula. Okay, So, by simplifying the equation, it then becomes this one lah. Ini ataupun yang ini. Okay, so you can then use this equation to find the total energy. Okay, ini untuk total energy. Oh, wait, Okay, so I think that's basically the theory. Yeah, so this is the theory for subtopic 9.1.